Hello everyone. In this lecture, we're going to talk about exponential family and generalized linear models, or sometimes known as GLM or GLIM. So this is not a particular machine learning model, but this is a family of machine learning models. And in particular, the generalized linear model says the conditional probability of your target is in the exponential family controlled by some linear transformation of x. Okay. So this is the exponential family and generalized linear models. So this is the family of distributions. And it turns out that it is a very wide family of distributions, just like exponential family. Most of the distributions like Gaussian, Laplacian, or maybe Poisson, or maybe discrete variables like Bernoulli or multinuclear, or sometimes known as categorical variables, or binomial or multinomial if the number of trials is fixed. All of them are exponential families. Of course, there are some functions that are not exponential family, like a uniform distribution over A and B. It's not an exponential family, but still exponential family is a very wide range of distributions. And if you can get some common properties of this family, then it automatically applies to each of its members. Okay. And then we will show that if you assume your target is exponential family controlled by linear transformation of your input, then it's a very wide family of machine learning models, and it also shares some common properties. And if you can derive that, it definitely applies to every family of the generalized linear models. And that also explains why we have the same derivative for the linear regression or logistic regression or softmax regression, and why all of them are convex, because the generalized linear model itself is convex. And of course, exponential family is convex in its natural parameters. Okay, so that is the roadmap for our next discussion. Exponential family, sometimes just write as EXP. So exponential family is a distribution on a variable x, okay? Controlled by some parameters either. So this is, if you have the exponential family, this is defined to be f of x, e of x, either transpose t of x minus a of either. It's again a giant equation. It looks like a headache, but it's easy to remember. So this equation tells you that exponential family is a log linear model. So if you take the log, it's linear in either, right? It's sort of the log linear model. So here T of x is known as the sufficient statistics. So statistics is actually a function of random variables, a function of random variables. And in particular, the random variable is x, okay? So the statistics is a function of random variable. For example, if my random variable is a real number, then maybe my sufficient statistics, it may be a vector, okay? It's a vector, so that's why you have the transpose here, it's a vector, okay? Maybe x squared or cosine x, as I like, as long as it's a function of your data, then it's a statistics. If x is in R2, then maybe my statistics are, for example, x1 times x2, or x1 to the power of x2. I mean, as long as it's a function of my data, or it's a function of the random variable, it's a statistic, okay? If it's a function of my parameter, then it's not a statistic. For example, in the Gaussian case, my mu and sigma, so the Gaussian, I know it's mu and sigma squared. So mu and sigma is not a statistics because mu and sigma are parameters. It's not a function of your data. It's not a statistic. But what if I have a few data samples, okay? X1 up to Xn that are sampled from the Gaussian distribution, then any function of X, okay, it's a statistic, for example. It's a statistic. or maybe I can say mean of x1, right? It's a statistic. So any function of your data is a statistics. Now, what does it mean by the sufficiency? If I say a statistic is sufficient, then my parameter will be independent of your data given that sufficient statistics. Okay, just like in the Gaussian case, the mean and standard deviation are sufficient statistics. If you know the mean and standard deviation, you can directly estimate your parameters. You don't have to look at concrete data samples. They give you no more information. You only need the sufficient statistics to estimate your parameters. Okay, the parameters are independent of your data. And for T of X here, you have the right to design what are the statistics. And if you put the probability in this way, then the statistics you designed here is sufficient. Okay, so statistics is any function of your data, and they are sufficient if your probability distribution looks like this. Okay, so in other words, you can think of it as some features of your data. Okay, or a feature of your data sample. Okay, it's a feature. So what is h of x? H of x is an unimportant thing. It's actually, if you estimate the parameter and if you take the log, the h of x becomes a constant. It's not very important. It actually you can think of it as a measure, right? So in the x-axis, maybe here the unit length is longer than somewhere else, and this can be controlled by h of x. Okay, it's actually squeezing or stretching your x-axis, and that is not an important thing. And you can think of it as some residual factors. It's not quite important. Then A of either is not a degree of freedom. Okay, so I'm defining a probability distribution on X whose parameters are either. So if you talk about probability distribution, it must be non-negative. So exponential of something is non-negative. So we say the h of x must be positive. Then it's also positive, then it's a positive, okay? But it's not necessarily normalized, right? So suppose I say h of x is x, and the sufficient statistics is x and x squared. Then I have the either 1 plus either 2 x squared. Then I say if I design my A either as, for example, is maybe 4.16 either plus maybe 3.2 either squared plus cosine either, okay? And when you integrate this term with x, okay, it does not integrate to 1, right? So that's why you have no right to define A of either. A of either cannot be defined. A of either is not a degree of freedom when you specify the exponential family. It's actually the log normalizing term. Okay. So the A of either is computed such that your P of x integrates to 1. So my goal is to make integral of x either dx is 1. Okay. So I'm saying h of x exp of either transpose tx minus a either is 1. Okay. And I can write things out. I say h of x exponential of either transpose tx, okay, divided by dx. Because it's exponential a minus b, so it's divided by exponential of b. So it's exponential of a either Cx is 1. Now you see this integral is with respect to x. So exponential of a eta is a constant. So I can put exponential of a eta there. So I say then a eta is log. Okay, it looks scary, but it's just a normalizing constant. And typically, we don't mind what is your normalizing constant, right? So you remember in the Gaussian case, it's important that it's exponential decay, and then it's quadratic in exponential, okay? Then the normalizing constant is not very important because even if you don't have the normalizing constant correctly, you just scale the probability distribution. And I know that the probability distribution must integrate to 1, so there must exist some like normalizing factor that make your probability distribution integrate to 1. So I can say, I can copy this term. So it must be computed in this way. Okay. So the domain of either it's not every real vector is valid, okay? The domain of either is such that the integral must converges. Okay, if it diverges, then it's not a valid either. Okay. So this is the definition of exponential family, and it's very intuitive. It says my distribution is a log linear model. Okay, log, then it cancels exponential, then it's linear. Okay, in terms of your sufficient statistics. Then you have some residual factor here, and you have a normalizing constant here. Okay? So it's easier to remember the exponential family. So we are now going to show that a very large range of distributions belong to the exponential family. For example, Gaussian. Okay. Let's assume my data x. Let's consider a single variate Gaussian. Okay, it's the random variable is just x. The mean is mu, and the standard deviation is sigma. The variance is sigma square is 1/2 pi sigma exponential of 1/2 sigma square x minus mu. Okay, it's clear that we have some exponential here, right? So it's good. So it's intuitive that we'll get the exponential family. Mu plus mu square minus 2 sigma square. Okay. So you almost get it, right? You almost get it. It's just here. You almost get it. Then I will say so now this time my sufficient statistics is x and x squared. Okay. So I call this is my T1 of x. Okay, the first sufficient statistics. The quadratic term is the second sufficient statistics. Okay, then this gives my first eta, and this gives my second eta. So this is actually either 1, either 2 transpose, okay, minus another term here, okay, mu square to sigma square. So this shows that the Gaussian distribution is an exponential family. So you say either 1 is actually mu divided by sigma square. Either 2 is actually 1 over 2 sigma square. Okay. So based on this, I can compute mu and sigma. So I just divide the both terms, either 1, either 2 is mu divided by sigma square. I'd rather do it slowly, otherwise I make an error. 2 mu, okay? So mu is minus either 1 divided by 2, either 2. And sigma square, I can say, sigma square is mu divided by either 1, which is mu is either 1 divided by 2, either 2 divided by either 1 is okay. Then obviously, you know, the A either term is minus mu squared divided by 2 sigma squared is actually this term. I don't have to compute it, okay? It's definitely a function of either only. It's not a function of x. Then h of x, you can say h of x is this term, constant. You can also absorb the term into the exponential and combine it with A either, right? It's not a problem. So the format is not unique, but it shows that the Gaussian distribution is indeed a exponential family, and the sufficient statistics are the x and x squared, okay? Then I have the parameters either 1, either 2 that can be represented by my usual parameters mu and sigma, okay? So I will say either's, so either now is a vector, is called natural parameters. Okay, it's more natural than the mean and sigma. So for the exponential family, so it's called natural parameters. And mu and sigma are actually the moments, right? Sigmas are the moments, okay, moment parameters. So a moment is some expectation of your data. So kth moment, okay, is the expectation of your data x to the power of k. Okay. So the mean, the average, is just the first moment. And kth central moment okay, you'd rather compute the expectation centered at the mean of the data. It's actually the expectation of x minus x bar to the power of k, where x bar is the expectation of your x. Okay, so take central moment. So now you see the mean and the sigma, the sigma square, they are the moment parameters because the variance is the second central moment. And the mean is actually the first uncentered moment. So it's actually the moment parameters. And there's some correspondence between the moment parameters and the natural parameters. So I have some function. I can map the function, okay, to the moment parameters. I call it mu in general, okay? And I can also have the mu, I map it to sigma, okay? So now I need a cheat sheet for the terminologies for these functions. So this is called psi, which maps from the moment parameter to the natural parameter. And the other way around is the psi inverse, which maps the natural parameter to moment parameter. So moment to natural psi. Moment to natural psi. This is psi inverse. So it basically says there's some correspondence between the moment parameter and the natural parameter. And it's not surprising because we are defining the same function. I'm just reparameterize your moment parameters. Now I'm going to show that a Bernoulli distribution is also an exponential family. So we remember that a Bernoulli distribution from Bernoulli parameterized by pi is actually saying the p of x given by pi, parameterized by pi, is actually pi to the power of x times 1 minus pi to the power of 1 minus x, where x is either 0 or 1, is the outcome of your Bernoulli trial, and the pi is the probability that it's 1, okay? So if it's 1, then you use the first factor, which is pi. If it's 0, you use the second factor, which is 1 minus pi, okay? So this is the probability of a Bernoulli distribution. I'm going to show that it's also an exponential family, but we know that exponential family has the exponential, but now here we don't have the exponential, okay? So how can I make this form into the exponential family? Okay, we must have some exponential here, but where's my exponential? So I can say, I just introduce the exponential and I cancel it out with log. Okay, now comes my exponential function. Because in the exponential family, I must have the exponential function. So I just introduce the exponential, I cancel it out with log. Then I will not cancel them out, because if I cancel them out, then I have done nothing. I would first compute this term, log of pi of x. That gives me x log of pi plus 1 minus log, 1 minus x log 1 minus pi. Right? So I can group things together as saying x log of pi plus log of 1 minus pi, okay, minus x times log of 1 minus pi. Right? Then I can group these two x terms here, okay? Log of pi minus log of 1 minus pi x plus 1 minus log 1 minus pi. Right? So this is the x term here. So this also shows that the Bernoulli distribution, even if it's a discrete distribution, it looks drastically different from a Gaussian distribution. It's also a member of exponential family, okay? Because it's exponential of something. In this case, it's x is my sufficient statistic. So I only have one sufficient statistic. As long as I can count the average, or as I can count the expectation of its being 1, then I know the Bernoulli distribution. I don't need the specific information of every data sample. Right? And this is my eta, my natural parameter. Okay. This is minus a eta. So a eta is minus log 1 minus pi. Okay. And there's also some correspondence between the pi and my either, right? So I say log of pi divided by 1 minus pi is actually either. So pi divided by 1 minus pi is exponential of either. Okay. Now I can say 1 minus pi divided pi, okay, is exponential of minus either. I can say 1 minus pi minus 1 is exponential of minus either. So I can move this minus term to the right-hand side of the equation. Okay, because it's originally minus 1, so I move to the right-hand side of the equation is plus 1. Then pi is actually 1 divided by 1 plus exponential to the minus either, okay? It's sigmoid of minus either, okay? So the sigmoid function comes out here. Definitely, we haven't done any machine learning tests so far. We're just defining a probability, but this shows that the sigmoid function comes out here. And then if you make some other assumptions in your machine learning model, eventually you will reuse the sigma function, and that's why you get the sigmoid function. And you have the same thing for the softmax. Okay. So in here, again, we can map the either to pi, and I can also map my pi to my either, okay? And you know, the pi is actually the expectation, it's the probability that your target is 1. So it's actually the expectation of your outcome x, okay? So this is also known as the moment parameter because it's the first order moment, okay? And we mentioned that if you map the moment parameter to your natural parameter, it's called psi. Moment to natural psi, psi inverse. Okay. So these two examples show that a wide range of probability distributions, even if they look very different, they, at least these examples, both belong to the exponential family, and it's indeed a very wide range of probabilities. Okay. So far, we just defined a family of distribution. When we define some concept, we must derive some property, right? Otherwise, we don't have to define it. It just introduces a new concept. If you can show a few properties that is useful for this family, then you can apply this property to every member of that family. So the first thing I'm going to show is the moment generating property. And I'm also going to show that the convexity and the maximal estimation being the same as moment matching. Okay, there could be other properties, for example, the sufficiency, but we are not going to show here. So by the moment matching property, I'm saying if you take the partial derivative of A either with respect to either, you get the first order moment. If you take the second order derivative, you get the second order central moment. So I'm going to take the partial derivative of A either with respect to either. Notice that either is a vector. It's the expectation, first order moment, expectation of sufficient statistics, okay? So it says If you consider the partial derivative of A either respect to either one, then it's just the expectation of the first sufficient statistic. If with respect to either two, then the second sufficient statistics. Okay. Where the expectation is set in terms of x sampled from my exponential family in that either, parameterized by that either. Okay. So this is my first order derivative. And the second order derivative is, so this is the Hessian, okay? The variance of Tx, okay? Where the x is also generated by the exponential family. Okay. I'm going to prove one. And definitely the first order derivative is much easier than the second order derivative. So I'm going to prove one. Where is my A either? Is that correct? I have to double check. Okay, I feel it's correct. So I'm taking the partial derivative of A either with respect to a particular either I. Okay, that's simpler when you consider the vector. So notice that here is the bracket, okay? So I'm going to take the partial derivative of A either I, then I'm going to take the partial derivative of the entire term, and the entire term, the most outer function is log of something. When you say the log of something, then I say 1 over something. Then I'm going to take the partial derivative of the argument of your log, right? Because it's the chain rule, so I'm going to take the partial derivative of this term. This term is the integral of something. And we know that the integral and the derivative cancel out, okay? Is that correct? No, that is incorrect, because the derivative is taken with respect to either, but the integral is with respect to x. They are different things, okay? So it's wrong. So you cannot say this is, okay? This is wrong because I'm not taking the partial derivative with respect to x. With respect to x, then it's correct. But it's not with respect to x, it's wrong. That's wrong. So rather, we should think of integral as a summation, right? You can think of integral is the limit of summation. Then if you think of the derivative of the summation of something, it's actually the same as the summation of the derivative, okay? So you can take the derivative inside of your integral. So I'm just going to write things out as the integral. I'm going to take the derivative here. And if you take the derivative inside your integral, then it's simpler. So you have h of x intact because it's a multiplicative factor. Then exponential of something, the derivative of exponential of something is itself. Okay. Then I'm going to apply the chain rule, and I'm going to take the partial derivative with respect to either I with of the exponent that gives you ti of x. So I would observe that the denominator is a constant, okay? I can make the constant inside my integral of the numerator, right? Because this x is different from that x. This x is a dummy variable, it's a placeholder saying I'm integrating over this variable, okay? But this x is not that x. So I can put my denominator within my integral. And that gives me integral of h of x, exponential of either transpose t of x minus a either times ti of x dx, right? Because a either, we mentioned that it's the log of the integral. Then if I move it out of the exponential, it gives me exponential of either transpose t of x divided by exponential of the log of the integral of something. So they cancel out. Then this term is just the denominator here. So this precisely gives me h of x exponential either transpose t of x minus a either. And we know that this is the probability of x parameterized by either in that exponential family, okay? And we know that if you integrate the probability times some function of something, or you take the summation of the probability of something and then the function of something, it gives you the expectation. So that is the expectation of your sufficient statistics, where the expectation is set in terms of your random variable generated from the exponential family with parameter either, okay? So the partial derivative of the a either with respect to either at that either is the expectation of your sufficient statistics of that exponential family parameterized by that either, okay? The either that you are going to take the partial derivative of. Okay, so this proves that the moment generating property, the first order derivative done. Second order, I don't want to do it here. It's a little bit more complicated than that, but it's not too bad. Convexity, I mean, if you agree with me, this is the variance of something, then it's positive semi-definite. Okay. But we also want to show that for any either one and either two in my domain of the natural parameters. So I say the domain of my natural parameters is the script n. Then I'm going to show that lambda either one plus lambda either two is also in my domain. And the key point of being in my domain is that the integral, okay, where you have the exponential of something, exponential of some either, okay, is okay, is finite. Then you can apply a Hülder's inequality, which says, I can actually, this term is actually less than or equal to this term to lambda plus dx times one minus lambda. Okay, because this term, this is my goal to show that it's less than infinity, but this term is actually e to the power of lambda either one transpose x tx times e to the lambda 1 minus lambda either 2 transpose tx dx. This is given by the Hülder's inequality. Then each of the term is finite. Then when you multiply them together, it's also less than infinity, then it shows that the domain is a convex set, and the second order derivative is positive, semi-definite, then it's a convex. The last thing I'm going to show in this video is that maximal estimation for exponential family is equivalent to moment matching. So these are two different paradigms for parameter estimation, but for exponential family, they turn out to be the same, okay? So I'm going to talk about moment matching first. So what does it mean by moment matching? Moment, I mentioned that the central moment, the uncentered moment, the kth moment is actually expectation of your x to the power of k. Okay, the kth order central moment is the expectation of x minus x bar to the power of k. Okay, where x is from the distribution, and in here, we're talking about exponential family, then it's the exponential. And x bar is the expectation, is the first order moment, okay? So this is the moment. So the idea for moment matching for parameter estimation is that you can compute the empirical moment. So let's say we have a Gaussian case. So suppose this is my Gaussian, okay? And suppose these are my data samples. Okay. So there are x1 up to xn. Now I can compute the empirical moment. I say 1 divided by m, the summation over m from 1 to capital M, xm, is my empirical moment, okay? So it's the moment counted from my data. And actually, the Gaussian normal is parameterized by mu and sigma square, okay? Mu is the model moment, the moment of your model, and sigma square is the second order central moment of your model. Now I'm going to match the model moment with your empirical moment, okay? Model your match moment with your empirical moment. I'm going to move this Gaussian around such that at some point, your first order model moment is the same as first order empirical moment. Then you get this point, okay? You just move your Gaussian around and you try to match the first moment. And likewise, you can squeeze it and try to match the second order moment. Then it gives you the parameter estimation, okay? This is the moment matching or the method of moment for parameter estimation. And this is, I think, what we have learned in the statistics course. And we're going to show that in the Gaussian case, or more generally in the exponential family, the maximal estimation is equivalent to moment matching. So I'm going to do the maximal estimation. Where is my likelihood? My data x. Okay, this is my model, my exponential family, where a eta is the log of my integral of h of x, exponential of eta transpose t of x, dx. Then I'm going to show the maximal estimation. So I'm going to compute the log likelihood of my data, okay? Log likelihood of my data with respect to eta is definitely the summation over different data samples, log of probability of that data sample parameterized by eta. okay? And for each of the parameter, then it's this, okay? HXM exponential of either transpose TXM for that data sample minus A either, okay? Then I would move the h of x out and say it's a constant, okay? So I'm saying I move this term out. I ignore that term temporarily. I'm just focusing on log of exponential, which cancels out as well. I only have this term. Plus some constant. The constant is not important, okay? It's a constant of either. It does not depend on my either. Then I'm going to take the derivative, okay, of this term. I mean, it's the derivative, partial derivative of root back to either vector. I can do it as a whole. So the derivative goes into the summation. And the derivative of either transpose T is TXM. Okay. And the partial derivative of A either with respect to either, I mentioned that it's here, the expectation over my sufficient statistics, okay? So that is my mu. That is my moment parameter mu. And I set it to 0. Set to 0 because I'm seeking for a closed form solution. I'm setting it to 0. Then I can say the m times mu is summation over m1 up to m t x m, where mu is 1 over m. Okay. So this gives me the Maximality Estimation for exponential family. Okay. And the mu is my moment parameter for this exponential family. And I mentioned that based on mu, you can use the psi function to get your natural parameter, okay? So this is the closed form solution for your mu. Then you are looking for the correspondence between mu and your natural parameter. There must be some psi there. Then it can give you the estimation for the natural parameter. But even if you don't, you still get the parameterization of the exponential family, right? You can either represent it by natural parameters or you can represent it by moment parameters. And this is precisely the moment matching or the method of moment for parameter estimation. Because this is the empirical moment and this is your model moment, right? I say the expectation over the sufficient statistics is my moment parameter, okay? And this moment is not empirical moment because it's from your model. The expectation is from your model. Then it's the model, the moment parameter, okay? So this gives us a useful result saying you don't have to try it again for moment matching for exponential family, including the Gaussian distribution, okay? So if you do the maximal estimation, it will directly gives you the moment matching. Okay, that's it for today. We talk about the exponential family. We show that a wide range of distributions belong to the exponential family, although there could be some distributions not belonging to the exponential family, like the uniform distribution between A and B as a continuous distribution. It's not an exponential family. And with the exponential family, you have some nice properties of the moment generating property. You take the derivative of the A ether, you get the first order moment. You compute the second order derivative Hessian of the A ether, you get the variance. And A ether is actually convex with respect to your natural parameter. And then the maximal estimation is also convex because this is convex. And then, this is linear, it's also convex, right? If you are considering minimizing, then if have the minus, this is linear term, this minus cancels out with that minus is plus, and then it's convex. So maximal estimation for the exponential family is also convex, and it has the closed form solution for the moment parameter, which is actually the same as moment metric. Okay. So in the next lecture, we're going to say, what if I define my target given some input as the exponential family whose parameter is some function of W transpose X, okay, some function of your goodness, then it gives me a conditional distribution of my target. Then it gives me a generalized linear model. And actually the linear regression or logistic softmax regression are a special case of the generalized linear model. Okay, see you next time.